Alright, let's go. Number 10. Rogue planets in interstellar darkness. Most planets are born within the gravitational architecture of a star system. Gravity gathers gas and dust into disks, planets assemble, and their orbits stabilize over millions of years. But not every world remains anchored to a star. During the chaotic youth of planetary systems, gravitational interactions can become violent. Giant planets migrate inward or outward, smaller bodies scatter, and occasionally a world receives a gravitational slingshot strong enough to escape entirely. When that happens, the planet is ejected into interstellar space, becoming a rogue planet. These orphaned worlds drift through the galaxy alone, sometimes for billions of years. Without starlight, their surfaces freeze to temperatures near 30-40 Kelvin. Atmospheres collapse. Oceans turn into kilometers of solid ice. Any complex chemistry on the surface effectively stops. Yet the real danger is not the cold, it is the invisibility. A rogue planet moving through the Milky Way can travel tens of kilometers per second. Over cosmic time, that is enough to cross entire star systems. If one passed through our solar system, its gravity could distort planetary orbits, scatter comets from the Oort cloud, and trigger a cascade of impacts lasting millions of years. The process is irreversible. Once a planet is expelled, it rarely finds another star. Astronomers now suspect there may be billions, possibly more rogue planets than stars in the galaxy. Silent, frozen, and almost impossible to detect. But even these wandering worlds are relatively gentle compared to what happens when matter itself becomes magnetically unstable inside a collapsed star. When a massive star dies, its core collapses into a neutron star, an object only about 20 kilometers wide, yet containing more mass than the Sunday. Gravity crushes matter so tightly that protons and electrons merge into neutrons, forming one of the densest objects in the universe. But some neutron stars are stranger still. A small fraction are born with magnetic fields so powerful they defy ordinary intuition. These are magnetars. Their magnetic intensity can exceed 10, 15, 15, 1000, and 15 Gauss trillions of times stronger than Earth's magnetic field. At that strength, magnetism does not simply guide charged particles. It reshapes the structure of matter itself. Inside a magnetar, the crust behaves like a rigid lattice of nuclear matter. Yet the internal magnetic field slowly twists and stresses that crust over time. Eventually, the tension becomes too great. The surface fractures. These events are called starquakes. In less than a second, enormous sections of the crust shift by meters, releasing energy equivalent to hundreds of thousands of years of solar output. The sudden rearrangement snaps magnetic field lines and launches a burst of gamma radiation across the galaxy. In December 2004, one such flare from a magnetar 50,000 light-years away briefly altered Earth's upper atmosphere. If a magnetar flare occurred within a few thousand light-years, the radiation could strip ozone from a planet's atmosphere and expose the surface to lethal ultraviolet radiation for decades. And the process cannot be undone. Once the magnetic stress releases, the crust has permanently changed shape. Yet even magnetars release their energy in brief flashes. Compared to what comes next, this is only a warning shot. Number 9. Magnetar Starquakes. When a massive star dies, its core collapses into a neutron star, an object only about 20 kilometers wide, yet containing more mass than the Sunday. Gravity crushes matter so tightly that protons and electrons merge into neutrons, forming one of the densest objects in the universe. But some neutron stars are stranger still. A small fraction are born with magnetic fields so powerful they defy ordinary intuition. These are magnetars. Their magnetic intensity can exceed 10, 15, 15, 1000, and 15 Gauss trillions of times stronger than Earth's magnetic field. At that strength, magnetism does not simply guide charged particles. It reshapes the structure of matter itself. Inside a magnetar, the crust behaves like a rigid lattice of nuclear matter, yet the internal magnetic field slowly twists and stresses that crust over time. Eventually, the tension becomes too great. The surface fractures. These events are called starquakes. In less than a second, enormous sections of the crust shift by meters, releasing energy equivalent to hundreds of thousands of years of solar output. The sudden rearrangement snaps magnetic field lines and launches a burst of gamma radiation across the galaxy. In December 2004, one such flare from a magnetar 50,000 light-years away briefly altered Earth's upper atmosphere. If a magnetar flare occurred within a few thousand light years, the radiation could strip ozone from a planet's atmosphere and expose the surface to lethal ultraviolet radiation for decades. And the process cannot be undone. Once the magnetic stress releases, the crust has permanently changed shape. Yet even magnetars release their energy in brief flashes. Compared to what comes next, this is only a warning shot. Number 8. Relativistic pulsar beams. When a neutron star spins rapidly and its magnetic field is misaligned with its rotation, it becomes a pulsar. Charged particles accelerate along magnetic field lines and erupt from the magnetic poles in narrow beams of radiation. Each rotation sweeps these beams across space like a lighthouse, but some pulsars rotate at astonishing speeds. Millisecond pulsars can spin hundreds of times per second. Their surfaces move at a significant fraction of the speed of light, and their magnetic fields accelerate particles to relativistic energies. Electrons and positrons spiral outward, producing intense beams of gamma rays, X-rays, and high-energy particles. If Earth were caught inside one of these beams, the consequences would be severe. The radiation would continuously bombard the atmosphere, breaking molecular bonds and generating cascades of secondary particles. Ozone could be destroyed within years. Surface life would be exposed to a constant storm of ionizing radiation. Unlike a magnetar flare, this danger does not arrive in a single burst. A pulsar beam sweeps past with clock-like precision for millions to billions of years. Some pulsars rotate every few milliseconds and maintain that rhythm for over a billion years as they slowly lose energy. During that time, anything within the beam's path is subjected to relentless radiation. Planets near such stars would struggle to maintain atmospheres at all. Molecules are gradually torn apart. Chemistry destabilizes. Biological complexity becomes nearly impossible. Yet pulsars still operate within the boundaries of stable stellar remnants. Their beams sweep across space, but they remain tied to their parent stars. The next phenomenon is far less predictable and far more violent. Number 7. Runaway gamma-ray burst jets. When the most massive stars in the universe reach the end of their lives, gravity wins in a spectacularly violent way. The stellar core collapses into a black hole, while the outer layers begin to fall inward. Under the right conditions, this collapse forms one of the most powerful explosions known, a gamma-ray burst. Instead of exploding evenly in all directions, the collapsing star channels its energy into two narrow jets that punch outward from the poles at nearly the speed of light. Inside these jets, matter and radiation become tightly focused streams of gamma photons and relativistic particles. For a few seconds to a few minutes, a gamma-ray burst can release more energy than the sun will emit over its entire 10 billion-year lifetime. But the danger lies in the precision. If one of these jets happens to point directly toward a planetary system, the beam arrives as an intense pulse of high-energy radiation. Gamma rays penetrate the upper atmosphere and trigger chemical reactions that rapidly destroy ozone. Within weeks, a planet's protective ultraviolet shield could collapse. After that, the consequences unfold over years to decades. Ultraviolet radiation from the host star floods the surface. Ecosystems destabilize. Mass extinction becomes likely. Evidence suggests that such an event may have contributed to past extinction events on Earth roughly 450 million years ago, though the case remains debated. The explosion itself lasts only moments. But the atmospheric damage it leaves behind can reshape a planet for millennia. And yet, gamma-ray bursts still come from dying stars, events that occur only occasionally within a galaxy. The universe has other mechanisms that do not wait for a star to die. Number 6. Cosmic radiation storms from supernovae. A supernova marks the violent death of a star, but the explosion itself is only the beginning. What follows can last tens of thousands of years. When a massive star detonates, it hurls stellar material outward at thousands of kilometers per second. The expanding shockwave plows into the surrounding interstellar gas, compressing magnetic fields and accelerating charged particles to extraordinary energies. These particles, protons, atomic nuclei, and electrons become cosmic rays. Once accelerated, they spread through the galaxy at nearly the speed of light, forming an expanding storm of radiation. Unlike the narrow beams of pulsars or gamma-ray bursts, cosmic rays diffuse through magnetic fields, slowly filling vast regions of space. If a supernova occurred within about 30 light-years of Earth, the radiation environment around our planet could change dramatically. Over hundreds to thousands of years, the incoming flux of cosmic rays would intensify. These particles would collide with molecules in the upper atmosphere, generating showers of secondary particles that reach the ground. Ozone depletion could persist for centuries. Increased radiation at the surface could alter mutation rates across entire ecosystems. Evidence from iron 6-0 isotopes found in ocean sediments suggests that nearby supernovae occurred within about 300 light-years of Earth, roughly 2-3 million years ago, briefly increasing cosmic radiation on our planet. The most dangerous part is the duration. Unlike a momentary burst, the radiation storm from a nearby supernova can endure for thousands of years, as the expanding shockwave continues to accelerate particles. But even this violence is still the aftermath of stellar death. The next phenomenon occurs when a star gets too close to something far more destructive. Number 5. Stellar tidal disruption events. At the centers of most galaxies lurk supermassive black holes, containing millions to billions of times the mass of the Sunday. Most of the time they remain quiet, surrounded by stars that orbit peacefully for millions of years. But occasionally, a star wanders too close. Gravity near a black hole is not uniform. The side of the star closer to the black hole experiences a stronger pull than the far side. This difference in gravitational force, called a tidal force, stretches the star dramatically. At first, the distortion is subtle, then it accelerates. Within minutes to hours, depending on the black hole's mass, the star is pulled into a long stream of plasma in a process astronomers call spaghettification. Nuclear matter that once formed a stable star becomes a ribbon of superheated gas thousands of times longer than the original star. Roughly half of this stellar debris is flung outward into space. The rest spirals inward, forming a rapidly rotating disk around the black hole. As the gas compresses and heats, it emits enormous amounts of radiation, often outshining the entire host galaxy for months. Temperatures in the accretion flow can reach tens of millions of degrees. X-rays and ultraviolet radiation flood the surrounding region. Magnetic fields twist violently, sometimes launching relativistic jets that extend thousands of light years. The destruction is absolute. Once a star crosses the tidal disruption radius, gravity ensures there is no return. Yet, tidal disruption events still depend on chance encounters between stars and black holes. The universe also produces objects that move with enough speed to escape entire galaxies. Number 4. Hypervelocity stars. Most stars orbit quietly within the gravitational structure of their galaxies. The Sun, for example, circles the center of the Milky Way once every 230 million years, at about 220 kilometers per second. But in rare circumstances, gravity becomes a slingshot. Near the supermassive black hole at the center of a galaxy, stars often travel in tightly bound pairs. When such a binary system passes too close to the black hole, the tidal forces can tear the pair apart. One star is captured into a tight orbit around the black hole. The other is violently ejected. The departing star can be accelerated to more than 1,000 kilometers per second, fast enough to escape the gravitational pull of the entire galaxy. These are hypervelocity stars, cosmic projectiles launched into intergalactic space. The process happens quickly. Within a few hours of the close encounter, orbital energy is redistributed, and the unlucky companion is flung outward at enormous speed. Over the next few million years, it will travel tens of thousands of light years across the galactic disk, eventually disappearing into the darkness between galaxies. If such a star carried a planetary system, the consequences would be catastrophic. Planetary orbits could be destabilized during the violent acceleration phase. Worlds might be ejected, collide, or spiral into their host star. Even if some planets survived, they would soon find themselves traveling alone through intergalactic space, where background radiation temperatures approach just a few degrees above absolute zero. And yet hypervelocity stars are still governed by classical gravity, an extreme rearrangement of orbital energy. The next phenomenon threatens something much more fundamental: the stability of empty space itself. Number 3. Vacuum phase transition bubbles. In modern physics, empty space is not truly empty. What we call the vacuum is actually the lowest energy state of quantum fields that fill the universe. Particles, forces, and even the properties of matter depend on how these fields settle into that state. But there is an unsettling possibility. The vacuum we live in might not be the absolute lowest energy configuration. It could be a metastable state stable for billions of years, yet not the true minimum. Somewhere in the deeper landscape of quantum physics, a lower energy vacuum might exist. If such a transition ever occurred, It would begin with the formation of a tiny region where space itself falls into this deeper energy state. Physicists call this a vacuum phase transition bubble. Once formed, the bubble would expand outward at nearly the speed of light. Inside the bubble, the fundamental constants of nature could change. The masses of particles might shift. Electromagnetic forces might behave differently. Atomic structures that once held matter together could become unstable. The boundary of the bubble, the phase transition front, would sweep across space at relativistic speed. There would be no warning. No radiation signal could outrun it. On cosmic timescales, the transformation would unfold rapidly. In just a few 100,000 years, such a bubble could cross an entire galaxy. Over tens of millions of years, it could reshape a significant fraction of the observable universe. And the change would be irreversible. Once the vacuum falls into a lower energy state, there is no mechanism to restore the previous laws of physics. Yet even this terrifying scenario requires a rare quantum event to trigger it. The next phenomenon may have formed naturally in the first second after the Big Bang. Number 2. Primordial black hole evaporation. In the first fraction of a second after the Big Bang, the universe was a violent sea of density fluctuations. Matter and radiation were compressed into regions so extreme that gravity occasionally overwhelmed everything else. In some of those regions, miniature black holes may have formed. Unlike the stellar black holes created by collapsing stars, primordial black holes could have been far smaller, sometimes with masses comparable to mountains or even asteroids. Their event horizons might be no larger than an atom. At first, they would seem harmless. Small black holes exert gravity like any other mass. But quantum physics introduces a strange twist. According to theoretical work by Stephen Hawking, black holes are not completely black. Quantum fluctuations near the event horizon allow pairs of particles to appear briefly. Occasionally, one particle falls into the black hole while the other escapes. The escaping particle carries away energy. This process is called Hawking radiation. For massive black holes, the effect is incredibly slow. A stellar mass black hole would take longer than 1060 years to evaporate, but small black holes behave very differently. The smaller the black hole, the faster it loses mass. As evaporation accelerates, the black hole becomes hotter and more energetic. In its final seconds, the radiation output skyrockets. The last instant could release an explosive burst of gamma rays equivalent to millions of nuclear weapons detonating at once. If such an evaporation event occurred within our solar system, the radiation flash would sterilize any nearby world, and once the mass is gone, the black hole simply vanishes. The process cannot reverse. Yet even this dramatic ending still occurs within the laws of our current universe. The final phenomenon goes further. It threatens the stability of reality itself. Number 1. False vacuum decay. Modern particle physics suggests that the vacuum of space is not just empty geometry. It is defined by the energy configuration of quantum fields, particularly the Higgs field, which determines the masses of fundamental particles. Measurements from particle accelerators indicate something unsettling. The vacuum state our universe occupies may be only metastable. This means the universe might be sitting in a local energy minimum, not the absolute lowest possible state. Somewhere in the deeper structure of quantum fields, a lower energy configuration could exist. If the Higgs field ever tunneled into that deeper minimum through a quantum fluctuation, the consequences would be immediate and unstoppable. A microscopic bubble of true vacuum would form. Inside this bubble, the fundamental constants of nature would change. Particle masses could shift. Nuclear forces might behave differently. Chemistry as we know it could become impossible. The boundary of this bubble would expand outward at nearly the speed of light. Nothing could outrun it, not radiation, not gravity, not information. From the outside, there would be no warning signal. The transformation would arrive at the speed of causality itself. As the bubble expanded, stars, galaxies, planets, and atoms would be rewritten by new physical laws. Structures that once held matter together might collapse instantly or fail to form at all. On cosmic scales, the expansion would be swift. Within a few 100,000 years, it could engulf an entire galaxy, and unlike every other disaster in the universe, this one would not merely destroy objects. It would replace the very rules that allowed them to exist. Across the cosmos, danger comes in many forms: wandering planets, collapsing stars, unstable quantum fields. Yet the remarkable truth is that for billions of years, Earth has existed during a quiet window of cosmic history. Stars have formed, galaxies have evolved, and life has had time to emerge and ask questions about the universe. For now, the laws of physics remain steady. And in that fragile stability, we continue exploring the most dangerous and most fascinating universe imaginable.